Thank you so much, Mr. Chairman. I'm going to talk about, I'm going to introduce you to some of you because maybe some of you know already the ionic liquids, but I'm going to introduce the ionic liquids as a sustainable alternative on energy storage. Okay, what's the purpose of this presentation? Renewable energies are crucial in the near future, but they have the intermittency. This is a major problem of the renewable energies. And in this case, what we have to use is the energy storage. Okay, how does a battery works? During charge, the lithium ion moves from the cathode to anode, and during discharge, the other way around, from anode to cathode. And the electron flows over the circuit to generate the electricity. Okay, we have the anode and the cathode. We have a separator on our battery, and we have an electrolyte that is like the media where the lithium ion can move from one electrode to another. And we want to change the common organic solvents by ionic liquid. We're going to see if they are even better than the organic solvent. What is in ionic liquid? Ionic liquids are salt that remains liquid at room temperature, composed of ions that result in a wide range of interesting properties in application. And the appropriate combination of organic cations and inorganic cations determines the properties of the ionic liquid. Some of the most interesting properties of ionic liquids are its low vapor pressure, almost negligible, high ionic conductivity, their thermal stability, very high, and the wide electrochemical stability. In a couple of years ago, a researcher, Andrea Balducci, stated that ionic liquids could be used as electrolytes in batteries because of their favorable properties, transport properties, its chemical and electrochemical stabilities, its low melting point and high boiling point, and its low vapor pressure. Ionic liquids cannot be used as pure electrolytes. We have to get a salt with electrochemical interest. In this case, we are going to study ethylammonium nitrate, okay, with different salts: lithium, magnesium, calcium, and aluminum. Okay. It's important to note that ethylammonium nitrate was the first discovered ionic liquid back in 1914, more than 100 years ago. Okay, and today is still studied as a possible electrolyte. Apart from the liquid state, in the recent years, solid state batteries are requesting a lot of investment. So in our case, we're going to study how can we make a solid state battery with ionic liquids. What do we do for this? What we're doing is to suppress the liquid state in a gel state, okay? We can do it in two different routes, an acidic route and a basic route with formic acid or ethanol, depending on the route that we're selecting. And we can pass from a liquid state to this kind of gel, very stable and with similar properties than the liquid state. Through this presentation, I'm going to talk about some different equipments, like structural analysis of density and rheology, thermal analysis like differential scaling calorimeter and thermogravimetric analysis, electrochemical analysis through ionic conductivity and different potentiostats, and also ecotoxicity with microtoxicity test and microcalorimetry. Okay, all of this together with the collaboration of the University of Porto. What do we do in the first term? One of the inherent properties of the ionic liquids is their solubility. So how does a salt behaves on an ionic liquid? We have studied this enthalpy of solvation and solution of different salts in an ionic liquid. Using these samples, you can see the size of the sample is quite tricky to work in here. And breaking the ampoule with the ionic liquid or the salt in different vessels, and relating the heat released or absorbed by our species, we can extract the enthalpy of solvation of the solution. We have performed a scientific paper published a couple of years ago with some molecular dynamic simulation, and we have observed that the enthalpy of solvation of ionic liquid, of this ionic liquid, the ethyl ammonium nitrate, is quite similar to the enthalpy of hydration of the water. Structural analysis has revealed that the density and the speed of sound is increasing monotonically when the salt concentration is increased. We have also, Professor Maria Villanueva has measured and analyzed the rheological measurements of this ionic liquid. In this case, is the pure one. And you can see how the viscosity decreases with the temperature as expected. We have also measured and determined the transition temperatures of this ionic liquid and these mixtures in a differential scanning calorimeter with this methodology under nitrogen atmosphere. Okay, you can see the range temperature is going about 80 degrees, minus 80 to 100 degrees. You can see here in black the pure ionic liquid. Okay, it presents a quite good crystallinity behavior. You can see here a cold crystallization followed by a melting crystallization. And you can see here that the concentration increases, lithium, calcium, magnesium, and aluminum. You can see how when the concentration of the salt increases, the crystallinity disappears, and there is kind of amorphous phase on our compound. Even in some cases, we can see the glass transition. Okay. The same occurs with the gel. You can see here the pure gel, we have a small peak of melting, but when we add the different concentration of the lithium salt, this crystallinity disappears, forming, getting our amorphous phase like compound. We have also measured or determined the thermal stability of our pure compound with lithium salt. You can see that there is practically no difference between the pure ionic liquid or when we add the lithium salt. And even the same with the gelation. There is practically the same thermal stability. You can see here a small decay on the curves. That is probably due to the small amount of water or the residual of formic acid or ethanol of the synthetic route. We have also performed the electrical conductivity by the electric spectroscopy with two different apparatus from more or less 10 millihertz to 1 megahertz on a temperature interval of minus 30 to 50 degrees in applied voltage of 0.2 volts. You can see here the electrode polarization related with the formation of the electric double layer. That is the immediate layer of the electrode when we are applying a voltage. Okay, and the conductive regime that is going to be our in our system. We're going to analyze this to see the imaginary part of the electric constant. Okay. These measurements were primarily done by my colleague Antía Santiago. And relating capacitance, dissipation factor, the vacuum permittivity, the area of the sample with the thickness of the sample, we can get the ohmic conduction of our compound, and we can get the electrical conductivity of the sample. You can see here the results. In the left is the liquid, and at the right is the gel. You can see this difference between the cooling and the heating. This is because of hysteresis, quite typical of ionic liquids because of the supercooling effect, that the melting and the crystallization does not fall in the same temperature. And you can see that the gel has even a bit higher ionic conductivity than the liquid sample. This is quite good result for us. We have also performed the linear sheet voltammetry of our compound. In this case, we have used counter electrode of glassy carbon, silver wire as quasi-reference electrode, and mercury as working electrode. Okay. You can see that practically there is no difference on temperature of our linear sheet voltammetry of the pure compound. When we're moving to this potential zero charge, quite important in the next slide to determine the density and the energy density of our compound. And this is quite important in the electric double layer compounds. You can see here the differential capacitance curves and here the potential zero charge that I was talking about. You can see that there is quite an asymmetric U-shape. This U-shape is the reflection of our asymmetry on our compound. That because ethyl ammonium is quite big than nitrate, and this nitrate and this difference is reflected in the curve. You can also see here the charge density curves that is the integration of our previous slide. And this is remarking the ability to store energy of our compound. Using a simple Helmholtz type layer model at the strange potential, it's possible to determine the thickness of the double layer. Okay, this layer that is subsequent to the electrode. Okay, and if we compare this with Kendra software, you can see that at the room temperature we have quite good similar values between simulated and the experimentally obtained. To determine the electrochemical properties of the gel samples, we have to use solid electrodes. In this case, we're going to talk about the glassy carbon electrode. You can see that there is practically no difference between the ethyl ammonium liquid and the gel half cell. And studying the capacitance curves, remember the ability to store energy of our compound, you can see that the gel sample, the doped gel sample with the lithium, presents quite big capacitance curves. We are studying these effects, and this is quite preliminary results, and it's quite tricky and interesting to analyze it. We have also measured, as I told, ecotoxicity of our compounds in the pure, in the liquid state. In this case, we are presenting a isothermal calorimetry that is able to detect 200 nanowatts of change in our system. And we are using soil samples, and we can understand how is the heat released by microorganisms on the soil when we add the ionic liquid. Okay. You can see here in black the control one without ionic liquid, and the other ones are with ionic liquid. So when we are adding ionic liquids, there is like a shift to higher times, to different times when we add the ionic liquid. Maybe like the microorganism are like stabilizing in this kind of new system. We have also measured the ecotoxicity through microtoxicity test with Salivibrio fisserii, a bioluminescent bacteria. And we can determine this toxicity through the luminescence relativity of this bacteria. Okay. You can see that this is the ethyl ammonium nitrate, the one as I was talking about. And this is the mixture with lithium, calcium, magnesium, and aluminum. You can see here that this is the harmless part of the graph. And most of the mixtures fall on the harmless part, okay? Just the case of aluminum that is falling in the moderately toxic, okay? current and future work. Maybe in the future, we are planning to measure different ternary mixture with organic co-solvents to increase these transport properties of the ionic liquids. But because even they are quite good, they can be improved with these organic co-solvents. Studying different ionic liquids like pyrrolidinium or TFSI cation-based, different silica-based precursors like polymer-based or functionalizing the current ones. Full cell experiments with lithium metal. This is the final test of our compounds, okay, to try it in a full cell battery. Toxicity evaluation over different trophic levels, we will see one later, like fish cells or even in seeds. And in the near future also to study water in salt solution. In a small amount of water, we have a high amount of lithium, and we have, this is quite a study right now on this kind of field. This is our most promising gel. You can see that the flexibility and the mechanical properties are quite good. As I told you, we are current, this is very preliminary results. We are developing and studying the seed reaction with the ionic liquids, okay? With different concentration of the ionic liquid. Okay, as I told you, this ionic liquid was discovered more than 100 centuries ago, 100 years ago, sorry. And in the current, in our group, in our research group, we have published just 9 research papers, okay, in maybe 7 or 8 years old. Maybe in the future we will publish, and it seems that we have a long way with this ionic liquid. Well, I want to thank my colleagues from Santiago. This is the gel again, the organizers, and thank you all for your attention.